while you're up there? Because this is I imagine you're pretty busy with your mission, and then you got this kind of the side project for you.
Yeah, we are extremely busy. Our days are scheduled right down to 5 and 10 minute blocks, and I have to find moments of opportunity to sneak down and get these photos. I did it because I'm interested in racing. I enjoy watching racing, and I just thought to myself, wouldn't it be cool if I took a few pictures from space? And then I thought, well, I don't think anybody's ever taken pictures of racetracks from space, so how cool would it be to get the whole 2018 season of tracks for not only IndyCar, but MotoGP and F1 as well. So that's my goal. I'm about halfway through all the tracks, so I've had some pretty good success, but I just thought it'd be fun, and it's really neat because I can watch the races on the weekend and send a picture out there, and the idea is that I can engage a different population, a new population for NASA, to get folks interested in what we're doing in space, and also share the fact that we have common interests with everybody else, and sort of join those two groups and maybe be a positive influence or positive experience and outreach for both sides of the fence, racing and space exploration.
And how's the mission going as a whole? I know you guys were out, bouncing around yesterday outside. How's it going so far? Nice pass.
Yeah, so the mission's going great. I'm on my last couple of weeks here, and we've done some phenomenal and diverse things. Everything from medical to growing plants to doing EVAs and then maintenance on our multiple systems. It's been a phenomenal experience, and having Drew and Ricky up here for the last part of it has been a wonderful experience as well. And watching them get up at 2 o'clock in the morning to go get pictures of the racetracks is kind of humorous. We make fun of him often, but he's getting some really good pictures.
So you mentioned you guys are scheduled down to the minute. So when you're not taking photos and you're not doing the mission, is there any downtime that you guys have, and what do you guys get to do with that kind of thing? How do you relax up there?
Yeah, absolutely. We do get some downtime each day. We get a little time, breakfast, lunch, and dinner. And then on the weekends, we get about a day and a half off on the weekends. So if we're not taking pictures, we're watching movies. And Scott and I and Ricky also enjoy playing music. So we've got a couple of guitars up here, and that takes up some of our time. We stay busy talking to our families, making phone calls, doing email, just sort of things you do on Earth. But we just can't go outside very easily and very readily. It takes a bit of planning to actually go anywhere but besides the confines of the space station.
There's a lot talked about the physicality of driving a race car, and we educate people on what it takes to do that from the physical side. Obviously, there are physical challenges being an astronaut, but when you're up in space for that amount of time, I imagine still training is a big part of what you guys do. So I assume some of your time blocks are dedicated to physical activity as well?
Absolutely. We train more than we fly. In fact, if you look at the amount of time that we as astronauts spend in space versus the amount of time that we do in our career, if you look at the ground time versus space time, space time is literally between 2 and 5%. Some people more, maybe up to 10% of your time, but really that's pretty rare. And everything we do on the ground is about training and mission support. And then while we're up here, we do a fair amount of training. Scott and Ricky and I just had a training session today for the capture of the upcoming cargo supply ship.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Welcome to everybody who made the trip out today. I just wanted to start off by saying we're really excited about the Orbital ATK-9 launch. The Cygnus is bringing with it over 3,000 kilograms of cargo to the International Space Station. Over 1,000 of those kilograms are on board to support the 50 science and technology demonstration experiments that we have, and 2 new facilities flying to the ISS. Today, we're going to be hearing about at least 4 of those different areas of science and technology demonstration going on board. And they range from doing atomic physics and quantum mechanics studies to studying some of the distant galaxies and X-ray emissions from those galaxies. The presenters today are going to be covering topics from the Cold Atom Laboratory, the coldest man-made spot in the universe, and they'll be on to talk about some of those atomic physics and quantum physics topics. The second presenters are going to be talking about using surface tension to separate immiscible fluids in zero-G, something that hasn't been tried before. We'll hear from folks who are doing the mixing and solidification of cement on orbit, and we'll see what that has happened to it when it's done in zero-G. And finally, we'll be hearing about a trio of Earth-observing satellites, CubeSats, that are going to be deployed from the NanoRacks CubeSat deployer and the GEM airlock. But first, I'll hand it over to my colleague from the National Lab and CASIS, who will talk more about those experiments.
Thanks, Kurt. So as Kurt said, we're super excited to be here. It's really pretty out here at Wallops, and it's super exciting to see a rocket launch. I want to remind you guys that when that launch goes and you're saying, you know, go Antares, go Cygnus, say go science too. You're going to hear from scientists today who have spent a lot of time, a lot of energy, blood, sweat, and tears getting their payloads ready for the spacecraft and to go to space. And they're really, really excited too. They're going to tell you all about their research. I'll tell you a little bit about the ISS National Lab. First of all, the space station is an absolutely incredible place to do research. And these scientists that are sending their research to the space station are super anxious to take advantage of some of the unique aspects of spaceflight, and that includes microgravity. It includes a vantage point with which to study the Earth, and also, not necessarily the case for these experiments, but putting experiments outside the space station to take advantage of a really, really harsh, extreme environment. So NASA and the ISS National Lab work together to basically open the door to researchers all over the world, in NASA's case, and then for the ISS National Lab all over the United States, to put research on the space station. And CASIS, the Center for the Advancement of Science and Space, with whom I represent, we are privileged to be able to work with NASA in this capacity and provide access to the research community that includes academia and student experiments. I believe we have over 20 student experiments launching. It includes industry, and so you'll hear from Zyput Industries, as Kurt mentioned, the continuous fluid flow separation experiment, and then also other government agencies, such as the NIH and NSF. So again, we're super happy to be here. We'll be able to answer your questions later, and I'll hand it back to Kurt to introduce our first science team.
Thank you, Liz. So first up, I'd like to introduce the Cold Atom Lab team. They're here today to talk about this new, unique facility on board the ISS and the amazing science that it's going to allow us to do for the first time. CAL, or the Cold Atom Laboratory, has been in development for the last 5 years, and I'll be handing the mic over to Dr. Kamal Odiri and, from JPL, and Dr. Eric Cornell from NIST. Dr. Cornell received the Nobel Prize in Physics in 2001 for his co-discovery or co-synthesis of the first BEC Bose-Einstein condensate samples in the world. So thank you, and here's the CAL team.
Thank you, Kurt.
Have our first slide. Well, it's a great pleasure to be here. I'm very excited about the rocket launch and about the things that are going to happen there. And could we click a slide forward? I can show you what's going on. I'm going to be talking about the Cold Atom Laboratory, COWL we sometimes call it. Of course, right there in the name is the word cold. We hope to get to, in fact, there is COWL on its way getting loaded into Cygnus. You can see it's on its way in. It gives you a feeling for about how big it is. Way down in the heart of that thing, and it's going to fly in the International Space Station. We hope to get to temperatures of about something less than 1 nanokelvin. So we intend to get to within 1/1000th of a degree of absolute zero. And I'm going to start right off by saying why, because why would you ever want to get that cold? And the answer has to do with really looking, if you look at the future, if you look at the trajectory of technology, of economics, of the technology that drives the modern economy, it's easy to understand that the future is in the direction of the very, very small. Small transistors, small computers, small nanobots. And at these very small scales, the physics, the science, the underlying thing that matters is called quantum physics or quantum mechanics. If you want to be able to design the technology that's going to underpin the economy of tomorrow, you have to understand quantum mechanics not just at the level of that junior level class you took in college. You've got to really get it. You've got to grok it. You've got to feel it in your bones. You'd really like to be able basically to see this stuff. And it's true that quantum mechanics is the science of the very, very small, but due to sort of a twist of fate, it's also the science of the extraordinarily cold. Getting extraordinarily cold has the effect of magnifying quantum mechanics up to the effect where you can see it. So you can actually see what amounts to waves of quantum matter a millimeter or 2 millimeters across. These things are called Bose-Einstein condensates. This idea, this sort of relevance, this connection between the very, very cold and the science which underpins the very small, which underpins the future of our economy, is not a new idea. In fact, there are hundreds of groups around the world here on Earth, including mine, which are studying this thing called Bose-Einstein condensation. With this idea in mind. But up in space, we hope to be able to get colder yet. And how do we get this cold? Here on Earth, we use lasers, which seems counterintuitive. Why would lasers make things cold? But they do. And then magnets to hold the atoms together and eventually let the hot ones pour out. And that's about, and we'll use all that same technology up in space. But in space, we can go one step further. And this final step is in some sense a step backwards to your high school chemistry class, where you may have learned that if you take a gas and you let a gas expand, like you put it in a cylinder and you gradually expand the cylinder, the gas inside cools down. It's the ideal gas law. And so you might think, well, why don't we just do this on Earth? We hold the atoms in a little magnetic box here on Earth, and we try to open up the box. But here, under the influence of gravity on Earth, you open up the box and the atoms pour out. Up in space, effectively weightless, microgravity, we can continue to open up the box, actually turn it off, and let the atoms expand gradually, just hang there, to the point to where we get the temperatures and durations of the experiment, which really aren't accessible here on Earth. We hope to get to a point well under a nanokelvin, and we hope to be able to see condensates and then later do experiments in these things over clouds which might be 1 or 2 millimeters across. Something you could really, we actually use microscopes and magnifying glasses and cameras to look at it, but in principle you could see with your bare eye. And therefore you get that kind of underlying intuition, which we think will be useful for science and technology in the future. And my colleague Kamal, do you want to?
Okay, thank you, Eric. As Kurt said, for being the first, you and your team to achieve Bose-Einstein condensate, on Earth, and now we're very excited that we are providing you an opportunity to even go cooler on ISS. So what Eric is holding is this is the heart of the instrument. It's a physics package. This is where actually we do all the we cool the atoms, and as Eric mentioned, we apply lasers and precise magnetic fields, and as the atoms are cooled when they reach maximum